Greetings and welcome to Chapter 7, Lesson 7.2, the Central Limit Theorem for Sums. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. You might be thinking, isn't this what we did last lesson in 7.1, Central Limit Theorem? Well, yes and no. We did Central Limit Theorem for averages, for the mean of groups of data from our population. So we took a whole bunch of samples from our population, and for each of the samples, we took their averages. And the result, by building a histogram, turned out to be a bell-shaped curve. Now, we can extend that idea for the Central Limit Theorem of Sums. The Central Limit Theorem of Sums says, hey, if you take these samples from your population and for each sample you add up the values, that sum of those individual samples will create a histogram of a normal curve, which is cool. So not only does the averages create a bell-shaped curve, the sum of those samples will also create a normal curve. Our mu sub x is still going to be our mean of our population. Our standard deviation of our population is sigma sub x. And we're still going to deal with going from an x to a z to a p. But in this time, instead of x's, we're going to deal with the sum of x. We're going to take the sum of x, then go to a z-score, then go to a p-value, the probability. So we're still going to have that middle step. The mean of our sum of x's is going to be n times the mean of our population. So before, it was our mean of our sample averages was the mean of the population. Well, now we're going to take the mean of the sum of x's is just going to be n times the mean of the population. The standard deviation of our sum of x's is going to be the square root of n times the standard deviation of the population. So square root of n times sigma sub x. Now let's get to the meat. What is z? In the past, z was x minus mu all over standard deviation. Well, now we're just going to deal with sum of x's and what our mean of the sum of x's is and what of the standard deviation of the sum of the x's. Plugging all of that in, we get z equals the sum of x minus n times mu sub x, all divided by the square root of n times our sigma of x. Time to run through an example by hand first. There are some keys to figuring out what you need to use for the central limit theorem and specifically for sum. So let's look at the problem description first. An unknown distribution, remember that's key to using central limit theorem, has a mean of 90 and a standard deviation of 15. A sample size of 80 is drawn randomly from the population. Find the probability that the sum of the 80 values, or the total of the 80 values, is more than 7,500. So anytime you see the unknown distribution, think central limit theorem. And if you are given some information about the sum of the values, then you're going to use the central limit theorem for sums. Let's find the probability that the sum of the 80 values is more than 7,500. So we're going to take the sum of our x's, change that over to z-scores, change that over to our probability. So sum of x to z to p. Taking our z formula, the sum of x minus n times mu sub x, all divided by the square root of n times sigma sub x. Now we're just going to plug in our values. Our sum of our x is the 7,500. Our n is the 80 values. Our mean is the population mean of 90. And our standard deviation is 15. So plugging in these values, we get 7,500 minus 80 times 90, all divided by the square root of 80 times 15. We get approximately 2.2361. Now we're going to go out on the web. We're going to go and find our Z to P calculator, and we're going to plug this value in to see what our P value is. We do want to keep in mind that we're looking for the probability that is more than 7,500. So this is a right-tailed probability. Keying it in, making sure that we're on a right tail, we get the probability that our sum is greater than 7,500 is equal to 0.0127. Let's now find the sum that is 1.5 standard deviations above the mean of the sums. We have a formula for this. In the past, we used x equals mu plus z sigma. Well, we're just going to say what our mean is now and what our sigma is now and plug these values in. And instead of just x, it's the sum of our x's. So the sum of the x equals n times mu sub x plus z times the square root of n times sigma sub x. Let's just plug in all the values for this. N is 80. Mu sub x is 90. Z is the 1.5 standard deviations away. Square root of n. And our sigma x is 15. So plugging all these values in, we get our sum of our x's will be 7401.2461. I know that's a little bit of work, and it is possible to do it on the TI-84. I'm not going to make a separate video on how to do it, but I will show you how to do it just in text. You would use the normal CDF with your lower value and your upper value, the mean of the sums, and your standard deviation of your sums. So plugging this in to normal CDF, our lower boundary is 7,500 because we want to know what's the probability that is more than 7,500. So 7,500 is our lower boundary. Our upper boundary will be our really, really big value of 10 to the 99. So in scientific notation, we would use 1E99. Our mean of the sums is 80 times 90. No, you don't need to calculate it yourself. Remember, it's a calculator, so it knows how to do it for you. You can use either parentheses to signify multiplication or the actual multiplication symbol. As long as it's in between the two commas, you'll be okay. For the standard deviation of the sums, that's going to be the square root of n times our population sigma, so square root of 80 times 15. Plugging that into our normal CDF, we get 0.0127. So we can do it on the TI-84 Plus for those that have access to the TI-84 Plus. For those that don't, do the example by hand. Follow those steps. It's time to do a full walkthrough of a problem. In a recent study reported October 29, 2012 on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15 years. The sample size is 50. Let's take a look at what distribution we're going to use. Now, because we're in 7.2, let's go ahead and use the distribution is normal for the sums by the Central Limit Theorem. That's what we're going to use. What are the mean and standard deviation for the sum of the ages of the tablet users? Now, we can't just say that the mean is 34. That's the population mean. That's not the mean of the sum of the ages. The standard deviation for the population is 15 years, but that's not the standard deviation for the sum of the ages. So we do have to do a little bit of math here. The mean for the sum of the x's is going to be n times the mean of the population. So 50 times 34 is 1,700. The standard deviation for the sum of the ages is going to be the square root of n times the standard deviation of the population. So square root of 50 times 15, in other words, 106.0660. All right, so we know our mean of the sum of the x's is 1,700, and the standard deviation of the sum of the x's is 106.0660. Now we need to find the probability that the sum of the ages is less than 1,650 years. We need to go from our sum of our x value to a z-score to a p-value. So our translation to the sum of the x's to the z will be z equals sum of x minus n times mu sub x, all divided by the square root of n times sigma sub x. Now we actually have n times mu sub x. That's the 1700 value. So you could just plug it in. We also know the square root of n times the sigma x value. That's the 106.0660. So you could also plug that value in. I just keyed in the raw values because that's what I was thinking at the time. And we get 1650 minus 34 times 15, all divided by the square root of 50 times 15. We get a negative 0.4714. That's the z value that we're going to have to use the calculator online to translate that over into a p-value. We know that we're looking for less than 1650, so that is a left-tailed test. And looking that up, plugging that into the calculator, we get the probability that the sum of x is less than 1650 is 0.3187. Now we have a new problem. Let's find the probability that the sum of the ages is more than 1,975 years. We're still going to use our same calculation for our z, but this time our sum of x's is 1975. So plugging in 1975 minus 34 times 15 divided by the square root of 50 times 15, we get a z-score of 2.5927. We're going to go back to that website, plug it in to find our probability. We do need to know that we're looking for more than 1,975 years, so that means it is a right-tailed test. We have to make sure which test we're doing, either a left-tailed or a right-tailed. Making sure it's on right-tailed, we get the probability that the sum of x is greater than 1975 is 0.0048. The next thing we want to figure out is we want to find the probability that the sum of the ages is between 1,500 and 1,800 years. So we need to find two z values, the one correlating with the 1,500 and the one that correlates with the 1,800, and then we need to find our p-values to those and subtract them. So we have a little bit of work cut out for us here. So let's throw it in and find the z-scores for the 1,800. 1,800 minus 34 times 15, all divided by the square root of 50 times 15. Plugging that in, we get 0.9428. For 1,500, we get 1,500 minus 34 times 15, all divided by square root of 50 times 15. We get a negative 1.8856. Now, these are not the values that we do more math on. We have to translate these over to p-values. We want the p-value that correlates with 0.9428. Now, we're going to do left-tailed tests for these. To find a mid-range, both of these are going to be left-tailed tests. 0.9428 translates over to a p-value of 0.8271. Negative 1.8856 translates over to a p-value of 0.0297. Subtracting these two values, we get the probability that the ages are between 1,500 and 1,800 is 0.7974. Let's just do a couple more calculations. Let's find the 80th and 12th percentiles for the sum of the 50 ages. So we need to translate the percentile of 80 and the percentile of 12 over to z-scores. So we're working backwards here. We have the p. We're going to go from p-value to z-score to then the sum of the x's. All right, the probability of 80 translate to a z-score of 0.8416. All I did was use a calculator online. The probability of the 12th percentile translates to a z-score of negative 1.1750. Now I'm going to take both of those z-scores one at a time and translate it over to the sum of the x's using our sum of the x equals n times mu sub x plus z times the square root of n times the sigma sub x. We have all these values. N is 50. Mu sub x is 34. Our first z value is 0.8416. Our square root of n should be a square root there. So square root of 50. And our sigma of x is 15. So plugging that all in, we get 2331.2. So 2331.2 for our 80th percentile. So our sum of our x's would equal about 2,331 in our 80th percentile. For our 12th percentile, we're going to plug in our z value of negative 1.1750 into our sum of x equation. Plugging those all in, again, sorry I missed my little square root marker, but I did do my math using my square root. I get my sum of my x's equals 818.75. So we know the 12th percentile is where the sum of the x's would equal 818.75, and our 80th percentile would equal 2,331.2. Good job, you've made it to the end of another lesson.